Hi, welcome to Quantum Physics for Non-Physicists. This is a recording of lecture 19, which took place yesterday, the 12th of November, and I wanted to re-record it, so I just spent 1.5 hours recording it, just to find out that it was not, in fact, recording all along. So I'll try to do it again. However, it is now lunchtime, so I'll be cooking at the same time, and you don't have to worry, because if it doesn't work out, then I will do it again later, which means that if you're watching this on YouTube, is because it did work out very well, so you're like post-selecting on a lecture that worked. This also means that all the things in the tablet are already written, and I'll just point at them, so we might go a bit faster than usual, but you can pause the video, or you can play it slower, etc. So today what we'll do is to do recap on measurements. So I'll just wrap up everything we know and all different ways of looking at a measurement, and we will then start with a section of thermodynamics, of quantum thermodynamics, and we'll just start very, very slow, just talking about what energy conservation means and how we can model a battery in the quantum case. And since we're starting with thermodynamics, here's an analogy that came to me from Twitter. I think the original author is someone called Alon Amit, which compares changing of bases in quantum mechanics with having a shower. So it has all to do with temperature and pressure and all these thermodynamics quantities, although not in a way that we will use them later. So what's the analogy? So on the top, you have access to two taps in the shower. One is the hot water and the other one is the cold water, right? So you can think of them as having two basis states. So H corresponding to 0 and cold corresponding to 1. However, this is not the basis that interests us when we have a shower. We are more interested in things like pressure and temperature. And what is the pressure? Well, pressure is essentially how much water is coming from the cold tap plus how much water is coming from the hot tap, right? So you can think of it a bit like the plus state, whereas temperature is hot minus the cold, right? Because cold lowers the temperature in general. So when you have a shower, what you do is kind of, you go from the basis hot-cold to the basis pressure and temperature. Okay, so we regulate the water such that we know what pressure and temperature are, which means that it's like applying a Hadamard gauge on the taps. Very good. So I have some housekeeping to do. The first thing is that there's some developments with the whole affair of this course not giving credits to the Masters in Computer Science. So this will be possible for next year, but not for this year. So if this is important to you, then you can take the exam next year as a bonus. This will probably also be safer health-wise than taking it this year, and I don't mind. Okay. So someone asked me for a link to have all the videos offline so that I don't need to watch the lectures live, and this makes sense to me. And so if anyone has already done this and has all these videos in some folder, please just send me the link. Otherwise, I'll do it in a couple of weeks from now, okay? So the other thing is that there will be projects in the group of quantum information theory. This will be announced very soon, on the 3rd of December. I think you could, after this course, you could easily do a semester project if you're interested in such topics. So you can just attend the information event on the 3rd of December. It's going to be online. I'll post a link, and then you can decide whether to apply or not. Yeah. Lecture notes. The first version of the LaTeX lecture notes will be available this week. And these were done by Lorenzo and Julia, who are two students of the course. And if you have comments, please send them to them. So I have not read them yet. I trust them, but I think they would benefit if you tell them, for example, there's a typo here, or this part should be explained better, or I didn't get this. So I will also get these comments as well. So please do send them this. Good. The last topic is a bit off, but it's that so I was listening to these lectures, to my own lecture a while ago because I wanted to know if I'd already mentioned something. And I was kind of surprised at the amount of ambulance sirens I could hear on the background. I live near a road that's busy, but not too busy in Zurich. So I thought that this could be maybe a nice side project for those of you in computer science, if someone wants to do it, which is just you have access to all these recordings of the lectures, and you could try not just my lectures, but many others, of which I guess most lecturers live in Zurich, or at least in a large city. And you can try to make a very, I think, relatively straightforward sound analysis to look for the sound of a siren going by. And then you can try to plot, the week of the semester and the number of sirens. And then try to map this, for example, to the Swiss COVID hospitalization plot. And I think this would be nice in itself, nice in a data analysis project kind of way, but also relevant today and maybe good to show ETH that it's a good thing to have online lectures for the time being. Okay, that's it outside science. So, what I want to do today is to recap all the ways we have of looking at measurements. So we'll talk about first, the measurements we've seen so far, they're all projective measurements. So we'll see about probabilities and projectors, the post-measurement state when we know the outcome and when we don't know the outcome, the observable representation of the measurement, and also this global unitary view of a measurement implementation. And then we look at two examples. One of them we've already seen is this kind of coarse-grained position. We've seen it a couple of times. And the other one is going to be a coarse-grained basis on 2 qubits, where we just measure the parity. Good, so let's think in general that we have a measurement that has m possible outcomes. We label them by k from 0 to m minus 1. So what is a projective measurement is one where the probabilities of getting some outcome k when you measure some state rho is given by the trace of some matrix, some operator pi k times the density matrix. And what do these operators need to satisfy? They need to satisfy a series of conditions, which we've not seen all of them in detail before. So the first one is that it's a projector, which means that if you square it, you get the same thing again. The second one is that they are orthogonal, which means that there's no overlap between them. So if you multiply two of them, two different ones, then you get 0. The third one is sort of a consequence of the other two. It's going to be that they are, of the other three actually. It's going to be that they are Hermitian. So if you take the transpose conjugate, you get the same thing again. And finally, they need to sum up to the identity. And why is that? This is just a normalization condition. And normalization just means kind of rescaling things. So in this case, we want that the probability of getting any outcome. So I make a measurement, I throw a die, and I want there to be one outcome. So the probability of any outcome should be 1, right? Not any specific one, but that there is an outcome overall. And because they don't overlap, this is just the sum of getting each of the outcomes individually, which is just the sum of this trace of the projector times rho for each of the projectors. Because the trace is linear, you can plug it inside. You can plug the sum inside the trace. And then using this normalization condition, you get the identity here. And then you just live with trace of rho. But because rho is a density matrix, is a quantum state, then this is 1, which is what we wanted. Okay, so that's where this normalization comes from. Good. Finally, and this will be useful for looking at the channel representation of measurements later on, note that this probability of getting an outcome, we can write it in a different way. So we can just add here another projector for free because of property number 1. Then you can pass one of these projectors to the other side because the trace is cyclic. And then you can replace one of these by the Hermitian, by the transpose conjugate because of this property. And then what you end up here, it's very much like, looks a bit like the one element of the cross decomposition of a channel, right? Where you have the original state, and then it's kind of conjugated by this, by these operators on the left and on the right, and on the right you have the transpose conjugate. So this is what we'll need. Sorry, let me here. Very good. So the example, like a non-trivial example that we've not seen before, is suppose you have two classical bits and you want to measure the parity. Okay, so you want to know if their sum is 0 or 1. So what are the options? For the sum to be 0, they need to either both be 0 or both be 1. Right? So it's even parity, or if it's odd parity, meaning that the sum is 1, they need to either the first is 0 and the second is 1, or vice versa. Right? So we can do the same in the quantum case to measure the parity. So you have a projector into the outcome 0. This is if both are 0 or both are 1. And remember what I mean by this is the tensor product of the 0 on the first and 0 on the second. So this corresponds to this matrix. Or the first is 0, the second is 1, plus vice versa. So that corresponds to this matrix. And from this matrix representation, you can see immediately that, well, if you multiply this matrix by itself, you get the same again. So it is a projector. If you multiply one by the other, you get 0. And if you sum them, you get the identity. Okay, so it does satisfy all these conditions for projector that we saw before. Okay. The other example we've seen a few times was this, just to have an example in a continuous case, is this coarse grained position. So now we have the Hilbert space being the line. And then you can think, well, in reality, we can never measure the position precisely to infinite precision. There's no way, it's not physical. Our measurement devices will always have some limited precision. So here, suppose that the limited precision is 0. So is L. So all you can tell is if the particle is in this box or this box or this box or so on, right? So I don't know, you could think of it as the size of a pixel in a monitor, for example. Okay, and so this corresponds to different projectors, and each projector K corresponds to having the sum of XX in some region, so from LK to LK plus 1, right? So for phi 0, this corresponds to this region here, for 1 corresponds to this region here, and so on. Okay. Good. And here we also need to show that this, give me a second, that these are projectors indeed. And for this, what we do is we need to compute the square of these operators, right? Which now they're not matrices in the traditional sense, but they're continuous versions. So if I do the square, you can look here. Here's the original one, and here's just a copy. So I just gave a different name to the variable x prime, and the integration limits are the same. So from LK to LK plus 1. Good. So once we have this, we just multiply them. Oh, I think I had this different originally. So you get this. Now, this thing here is a number. So you can kind of move things around, which is what I did. I just moved this back there. Okay, and this number is the delta between the two. So you get rid of one of the integrals, and because they have exactly the same integration limits, what you end up with is the original. It's the original projector. Now, if you've chosen two different ones, so two different values of k, what would happen is that here there would be a different value. So there would be no region of overlap where that would give us a non-zero value here. Okay, so in the end we end up with 0. And if you sum all of them, then you just get again the whole line. Very good. So the other thing we saw was the post-measurement state when we know the outcome k, and we saw this to be we saw this to be what? Well, just the projection of the initial state divided by some normalization factor, which is just the probability of getting this, right? And that's just because we want, in the end, that this state has again trace 1. And for pure states, for the special case of pure states, that was this thing here, where here we need to have the square root of the probability of measuring. And I'm sorry, I think in one of the first lectures I forgot the square root. This should now be fixed in the lecture notes, if not in the handwritten notes. Okay, because I don't know where I put it. However, if you find it, please let me know. The reason why I forget it is because in quantum information we always work with the density operator, never with the pure states. So just a way to memorize it is that with the density operator we have probabilities everywhere, and with the square root we have with the pure states we have square roots of probabilities. Okay, so this is the post-measurement state. This is how we update our knowledge of the state, given that we know the outcome to be this. And why is that the case? That's because what we know about a measurement, at least a projective measurement, is that if we made the same measurement again, we should get the same outcome, right? So if you throw a die, you get 5, you close it and you look at it again, you should see 5 again, right? It's not like you're rethrowing, but if you make the a consecutive, like just looking at it as it is. And one way to achieve this is, or the simplest way to achieve this is precisely by just projecting into the outcome. Okay, this is if we know the outcome. And an example, if we have the particle in a line, this is kind of the wave function square, so the amplitude of the wave function, but the generalized version for the density operator. Of course, not all the information about the state is here for mixed states. But just to say, if we measured it and all we got was the outcome that it's in this box, then the post-measurement state will be 0 outside the box, and here exactly this, but renormalized, so a bit larger. Okay. Good. So what happens if we don't know the outcome? So just to summarize, but now to come at it from a different direction that we did in the class. Where's the salt? Salt. Okay. So suppose that Alice makes a measurement. I know that she made a measurement. I know exactly which measurement she made, but I don't know the outcome. Right? So all I know is that with probability k, she got outcome k, and in that case, the final state is rho k, this post-measurement state we saw. So now we just replace this rho k with what we saw before, and the probabilities cancel out because it was just a normalization. So you get just this sum over the projected versions of the state, right? And this, as we saw before, we can see this as a channel acting on the system, a quantum channel acting on the system. And this is kind of the channel view of the measurement. So a local view of the measurement. When we don't know, we don't look at the memory or the pointer where the outcome is registered. We look just at what happens to the system itself, right? And this corresponds exactly to the cross operation decomposition of the channel, where each of the cross operations is precisely this, the projector, and it satisfies the normalization condition for the cross operator. Yes, for the cross operators, because the projection operators are normalized. I need to put some water here. Okay. So from here, we went to the observable representation of a measurement. And at the time, the first time we talked about it, I told you that this is just one way to look at it that allows us to compute some quantities like the average position, for example. But later today, we're going to see the physical interpretation of it. Okay. So the idea of the observable representation is just to take all of these projectors and just turn them into a matrix. So we give one label, which is a number to each of them, which we usually think of this as the outcome, right? Now, each of these projectors, because of the way they are defined, the properties they need to satisfy, they can actually be expanded in some basis, such that if you sum for all of them, you get an orthonormal basis, right? So in the example of parity that we saw before, we could think of this being like 0, 0 plus 1, 1. Here you have 0, 1 and 1, 0. All of them together, they form the computational basis for 2 qubits. And this is in general the case. Also here, right? You can think of it as this, you can expand each projector into a basis, and then you can bring them all together and they form a computational basis. Okay. So again, you can then take the observable representation and just take these projectors and expand them in their basis. Okay? And this will be useful later on in a minute. Okay. But for now, we don't have to worry much about it. But what matters is the sum over all outcomes of the label for the outcome, and then this projector that can be expanded like this. Good. And then it could compute some quantities with this, like the average. And we saw also things like the variance. I think those are the only two we looked at for now. Okay, so what are, in the examples that we saw before, what are the corresponding observables? So for parity, we can choose 2 possible labels for each of the outcomes. Okay, let's not choose 0, otherwise it's you could, but it's just harder to look at it. So we choose +1 if the parity is 0 and -1 if the parity is 1. We sum the 2 projectors and we end up with this matrix, right? So this is the observable for parity, and you will work with it in the tutorial. For the position, we saw that if you have like infinite precision, then we can look at the position as this, where the label is just x itself, the same x as we put there. But think that if instead of measuring in millimeters, we want to measure in centimeters, then we just divide this or this x by 10, for example. Okay. Now the coarse grained position that we saw before, so we have the sum over each of the projectors, and then in the label for each of the projectors, some xk corresponding to this. So in this case here, this choice is arbitrary. Different choices will give you then different results, but you can do what you want. So in this case, I picked the xk to be k times L, which corresponds to kind of the beginning. So this would be the xk for this. This would be the one for 1. This would be the label for this one. Okay, you could also choose, for example, the value in the middle of each box. Okay, maybe this would be more sensible, but I just picked an easy one. So in this case, you get the sum over all k, KL, and then indeed the projector here. Good. Then the other view we looked at was this global unitary view of the measurement. And this is the idea that we really want to look at the physical implementation of it. And so we look, we consider 2 systems. This is our system that was measured, and then some other system that will be a pointer. And we saw some examples of this. We'll get into this later. And then we just saw, well, we pick some coupling, some interaction between the 2 systems that will connect to the things we want to measure. So we choose the observable we want to measure on the first system as this local Hamiltonian tensor, some operator on the pointer, and we'll see later what properties this operator needs. And we'll see some examples later. So from here, we can build the evolution operator, the evolution unitary, which is just the exponential of this with time and h bar. And then we can apply it to the state. So here we consider the easy case where you have an initial pure state, and you can consider more generally a mixed state in the system. And for projective measurements, for now, it's better to have a pure state in the pointer. So we have any pure state in the system, and we can in particular expand it in this basis jk that we saw before. So this would be the basis of the this basis of the observable, right? And the coefficients will depend on the initial state. But again, you can have it a sum over k of sum over the little jk's of this. So what happens when we apply this unitary on this state? So on the first system, AS will just act here, and this is going to be an eigenstate with the eigenvalue lambda k. So the lambda k comes here to the exponent, just like we saw before for the simple case of basis measurement. Yeah. And what is left on the second one is still this MP. Right? So in the first system returns the initial state, but now we have this exponent of the eigenvalue of the label, and then you have this. So this is what's acting on the second, on the pointer. Okay? So if you look at what in the first system is a sum of k, and then these are the only things in the whole state that depend on this jk. And what this corresponds to is exactly, you can do it yourselves to verify this, is exactly if you apply the projector over k to the initial state. Right? So you have, this is initial state, you apply the projector over k, which was, let's see, which was this, which means that only the terms jk for the same k will survive. So you end up with exactly this. So you get the sum over k of, in the first system you have the projector over the initial state. In the second system, in the pointer, you have this thing here, which we're just relabeling. We're just relabeling phi k, okay, on the pointer. So what's the condition for this thing to describe a projective measurement? Well, for this to be a projective measurement, then I need to satisfy that all of these states here are orthogonal. Okay. If all of these states are orthogonal, then we can see, and maybe we'll show this in a later tutorial, or you can very directly see by hand now, that if you take the partial trace over P of the final state, of this state here, then what we get in the system is going to be, it's going to be exactly this. So the sum over k of all the projected versions, which was, if you remember from before, so if you take, so this thing here is our row initial, then this is exactly the channel version of the measurement that we saw before, from coming from just the information theoretical view, right? If they're not orthogonal, then what will happen when we try to do the partial trace is that there will be some cross terms, and what you'll end up with will not be as clean as this. So you'll do an example of this in the tutorial this week for the case of the qubit pointer. Good. So what were some examples of pointers that we saw? So first we saw two possible pointers where the pointer is a particle in a line. The first one, our operator m that acted on the pointer was just a momentum operator. Right? And we saw that by coupling, so the observable in the system to the momentum operator, what we got was this shift in the wave function of the pointer depending on the label of the observable for each outcome k, right? So if you started with some pointer, I don't know, like a Gaussian, but a Gaussian that's truncated somehow, then you'll end up with this being phi 0 and this being phi 1, this being phi 2, and they're kind of centered around something that is determined by the eigenvalue of the observable, but also by time. So if you're watching it in real time happen, so you turn on this interaction and you slowly see all of these peaks kind of coming apart. You don't see them. You see them in your simulation. You don't see this happen in real life. Yep. So then you measure the position of the pointer, and if I get, for example, this outcome for this x, because they're all orthogonal, there's no overlap here. I chose the initial stage and the evolution time such that they really separate. Then I know that this corresponds to having the outcome in my system that I measured being 1, being 2 in this case. Oh, sorry. Let's put here 0, 1, 2. Okay, better. Good. So, the other example we saw was instead of coupling it to the momentum, we couple it to the position of the pointer. And then we see a similar shift, but instead of being now in the position wave function of the pointer, we see a shift in the momentum wave function of the pointer, which means that we get a kind of a kick in momentum, we increase or decrease the momentum of the particle depending on the eigenvalue of the observable. We saw this being applied, for example, in the Stern-Gerlach experiment, right? Where we got here, we send a spin particle, it could be spin up or spin down or a superposition thereof. Through here, there was some interaction that coupled the spin to the position, giving a kick in momentum, which meant that either the particle now wants to go up or wants to go down, depending on the spin. And in order to measure this in some position, in some detector, we need to let this particle evolve, for example, free evolution like we saw before. And then eventually it hits here. And if we know that if it was here, then the spin was, I think, down. If it was here, then the spin was up. Okay. And the difference in sign between this and this is because one is the inverse Fourier transform of the other, right? And I think this is the right direction, but it could also be the other way around. Okay. The other example we saw was when the pointer was just a qubit, and we saw, for example, the whole interaction, the unitary being a controlled knot, right? This was one of the cases we saw. The case you'll do in the lecture, in the tutorial this week, is going to be to use a rotation over x, x for theta, and then you need to be controlled in the systems you want to measure, such that if the parity is 0, you end up here with the state 0, and if the parity is 1 up there, then you end up here with the state 1. So this will be something for you to play with. Good. To see that, you know, the main takeaway is that the R pointer does not need to be a particle. And again, this whole idea of modeling the pointer explicitly is just to kind of push away this imaginary boundary between the quantum world and the classical description, right? In the quantum world, we have unitary operations. In the classical description, we have probabilities of getting some outcome, right? So here what happened is that at the end we measure this, right? So here's the boundary between quantum and classical. In this case, at the end, we measured this particle, right? And we get some probabilities of being here and some probabilities of being there. But we don't do this kind of hard measurement on the system itself. Yeah. Again, where we put this boundary is arbitrary. It can give us a better understanding of the underlying physics, but eventually you could bring this boundary as far up as you'd like and get different kinds of problems depending where you live it. This is what we talked about when we talked about Schrödinger's cat and Wigner's friend a long time ago. Good. Now there's another type of measurements that are non-projective. And the example that we've hinted at before was, for example, if we do this evolution, just like we saw, but now these states are not orthogonal. Okay? And one reason for them to be non-orthogonal could be that maybe the original pointer was too spread out. It was a Gaussian, it was too spread out in position. So after evolving for a while, then there's still some overlap between the different eigenstates. So if I measure now position of the particle of my pointer and I get this value, I still don't know if it corresponds to this state or to this state. I could think maybe it's more like it corresponds to this than this, but I'm not sure. In this case, the map that you get on row S is not going to be as neat as before, so it's not going to look exactly like this. And you'll do an example of this in the tutorial. Not for this pointer, but for the qubit pointer. Good. So what are other reasons why? What are other reasons why the measurement would not be a projective measurement? So we saw maybe the pointer is too wide, maybe we don't let it evolve for long enough, or maybe we wanted to apply this evolution, but we can never really implement a unitary evolution in the lab. There's always noise that we don't account for, so we always have just a map description, a non-unitary map description of the things we can actually implement. Or, maybe the initial state was not a pure state on the pointer, because we can never really prepare a pure state in the pointer. There's even cases where we do want to make the measurement more ambiguous on purpose, because we don't want to disturb the state of the system by a lot. This is what is called the weak measurement. Okay. So there's many reasons. In fact, like projective measurements are a fantasy, they're an idealization. We can never implement them in practice, but they're very useful idealization. Good. For this more general case of measurements, the physical ones, we have the mathematical tools to treat them. I will just mention now that they exist. I'll say their name. You'll try to compute this representation for a very simple example in the tutorial, but we'll not get into detail over this because we need to move on with other physics parts of quantum mechanics in the lecture. Okay, so the more generally, so measurements can be represented by POVMs. This stands for positive operator value measure. Which means what? So we represent again the measurement by some operators, some matrices, where the probability of getting an outcome is still the trace of matrix times the density operator. But now the conditions we impose on them are weaker than before. So we don't impose that they are projectors. We still impose that they normalize, so that they sum up to the identities, so that for the same reason as before, so that the probability of getting any outcome is going to be 1. And we ask that they are positive. This again is physical implications, right? But we don't ask more than this. Good. So with this, we can compute the probabilities of getting outcomes. Now, they do not uniquely specify neither the physical implementation nor the post-measurement state. They're just a way of giving us the probabilities, right? So in order to get the physical implementation, the post-measurement state, we need to look at which channel actually implements this. What are the cross operators of this channel, which again depend on the kind of dilation of the channel to a unitary in a larger system. And from there, we can build the cross operators, then build find these POVM elements. So if you have the physical implementation, you can find the POVM elements. If not, then there's some freedom. And the reason is that in order to get the physical implementation, at some point we need to take square roots of these operators. And these are complex matrices, so there's many possible values. Square roots which will correspond to different implementations. To learn more about this, take the quantum information theory course this year or next year. Okay, again, this is a very, very rich field. The field of measuring and sensing and quantum physics is very rich. There's also this course next semester by Misha Woods, where you will also work with POVMs, and it's a lot of fun, but it's not the fun we have time for right now. So we move on, and we're going to start talking about quantum thermodynamics. And don't worry if you don't know anything about thermodynamics yet. You don't need to follow this discussion, and I will tell you the essential things. Okay. So what is thermodynamics? So you can think of it, maybe let me go back to just an empty page so you don't start reading what's there yet. So you can think of thermodynamics as kind of accounting, but accounting for physical quantities. Like you have a very complicated process and you have some things of interest like energy. I want to keep track of all the energy flows in this process. Maybe an analogy for computer science would be if you have a very large network and you want to keep track of how many packages are sent through which channels, or you want to keep track of the information flows within your network. Okay, so it's a similar thing, but now for just apply it to some physical quantities of interest, which will be defined for different types of systems. The other thing you need to know about thermodynamics is that it was conceived as kind of an empirical theory, by which I mean, physicists saw, for example, a gas, and they thought, okay, a gas is composed of many, many different particles. In the end, the state of the system is very complex. All these particles are moving in different directions. It's like the average speed of the particles that determines the temperature, for example. But I will not care about anything of this. I'll just care about some simple properties of this gas, right? So I'll just characterize the gas by things like the temperature and the pressure and the volume, for example. And let's see if by taking just this macroscopic view, it's enough to characterize all these flows that I'm interested in if I have a global system. And it's very, very successful as a theory. The other thing about thermodynamics is that it was, there's physics that we do because we want to learn more about how the world works, like astrophysics. I want to know how galaxies move. I want to know what planets are made of. Maybe I don't have any specific application in mind, but I just want to understand how it works. Thermodynamics was not this, right? It's a very, very pragmatic theory. It was invented by people who wanted to build machines and wanted to know how efficient these machines could be. How can I make a train? How much coal do I need to burn at what temperature to move this train from London to York, for example? So it's a very, very pragmatic theory. So it's surprising that we can do something when we take it to the quantum limit. Okay, so quantum thermodynamics as a field it's always been there floating around from the beginning of quantum theory, but it's only been fully developed in the last 15 years or so. So let me, I don't know what to do with this page. I do. And now let's go back there. Okay. So what we'll do today is to give you some ingredients for quantum thermodynamics, and keep in mind this ideal goal, which is kind of keeping track of where energy is going, where different other quantities are going, trying to build machines, like trying to build very small fridges, for example. Yeah. And trying to transform between different types of energy, like the energy that exists in a flame to the energy that exists like in a chemical battery to the energy that exists, just on a train that's moving. How do we convert between these different things? Okay, so the first ingredient that we need is some notion of work. And what work means is kind of well-ordered energy. An example is a battery that you know exactly how much energy you have stored in there. Another example is electric current. So you know the frequency, you know the voltage, you know the intensity, etc. And you have all these devices that are made, like a charger, a laptop, etc., that are made precisely to use this energy very, very efficiently. Okay? As opposed to, for example, like we saw before, the energy that exists in a fireplace. Right? I know that there's fire there. I know that it's hot. In principle, I could try to build some engine to use this heat to boil some water, to move something, etc. But it's not immediately clear how I do it. Okay, so think of work as just like energy I can use right away. So the simplest classical example is a weight, like that's very good. So like think of a rock that I can lift and I can keep like hanging somewhere at a certain height. Okay, so this is the height and this is Earth down here. And what can I do with this rock? Well, I know gravity pulls down and this comes for free. So if it's hanging here, then at some point I could, for example, connect it by some pulley system to, I don't know, a little train and move this train by some amount. And then I end up with the rock here. Then I can use it another time and end up there, and eventually it hits the ground. And then it's like, I can't use it anymore in this way. I would have to, you know, put some energy into lifting it again. Yeah. So that it's very used, this kind of example, in thermodynamics by thinking, I don't know, I let a gas expand and this pulls this thing down or up, for example. So we think this as like our goal. We want to have something that works a bit like a weight. By the way, the reason why the ground state in Hamiltonians is called the ground state, that's like the state of the eigenstate of the least energy, is precisely because of this analogy to having a weight using potential energy, potential gravitational energy, meaning just that you can use it like this. So the idea is that eventually when it reaches the ground, it's down here and you cannot use it again. Right? You cannot keep using it without putting some work in. So this is the ground state. It's the state of like least energy. Okay, so what's a quantum example of such a simple battery? Well, we can think of a Hamiltonian, which for now, so let's take a system that is discrete, but it's infinite. Okay, and let's take a Hamiltonian for this battery that is just kind of linear on this level. So for each eigenstate Ek, the corresponding energy is some fixed delta multiplied by K. Okay, so this is like, you see here energy, these are the possible different eigenstates, and this is their energy. It's kind of linear and very neat. Okay, and the spacing is delta. And in the ideal case, we want to make this delta very, very small. This corresponds to being able to move this weight by a very, very small amount and using only a little bit of this energy. Okay, in the quantum case, this will be even more dramatically important. We'll see an example soon. So, by the way, this is not a physical Hamiltonian because it doesn't have a ground state, right? It's the same as having this this weight here, but there's no Earth under it, right? Where's this gravity coming from? So it can just keep going down forever. So eventually our battery will have to have a ground state, but for the analysis that's following, it's simpler to consider this case, and then later we can make the corrections if you make this k going not from minus infinity to plus infinity, but going from 0 to plus infinity. Okay, so just to have this in mind. So if I have the initial state of the battery being up here, Ak, then what is the energy of this? So the energy, if you remember, is this, the average energy is the expectation of the Hamiltonian. And if you replace this Hamiltonian here, and here we have this Ek, then what you get is precisely K times delta, right? So the average energy is this. And in this case, it's a pure state, that's an energy eigenstate. If you look at the variance over energy, so this delta E squared, then you get that it's 0 in this case. So this is like the perfect case of exactly I have a weight here and I know exactly where it is. I have a battery like an AA battery and I know that it's exactly full. Right? It's not very realistic. Normally you have the battery and you know I've used it for an hour. I know it's more or less in this range of energy, right? But we'll start from this idealized model. And now, how do we use this to keep track of energy changes? Let's consider a simple case where we just have two systems. And now for this example, this first system can be a qubit. Okay. And later on, I mean, most of what I'll say is general, but then the example we see is just for this qubit. Okay, so we have the qubit and then this battery. Here's the battery. And the qubit, well, it will have some Hamiltonian, and we just call the eigenbasis of this Hamiltonian, just relabel it as the computational basis. Okay, just call this 0 and this 1. And we kind of rescale the Hamiltonians. It's, you know, it's still general. But I just say, well, this is energy 0 and this is energy epsilon here. So Hamiltonian is this. And because this is 0, it just goes away. And I'm interested in questions like, think of the classical example would be, if I want to move a train by a certain amount, how much energy does this cost me? So here it's going to be, if I want, for example, to flip my qubit from 0 to 1, how much energy does it cost me? Okay. So how do we account for this? So again, let's think of an example like you have a battery-powered drone, and you want to know how much energy it costs you to go from, I don't know, from A to B, from some point to another point. Well, what you can think is that overall, if you think of the drone and the battery and the system overall, that overall there's conservation of energy. All the energy that the drone spent, it took from the battery, right? So the idea is going to be that I'll impose that overall, the overall operation is going to be energy conserving, so that if I need some battery here, it's some energy in my qubit, it's going to have to come from the battery. Good. And we'll see some example of this in a moment. But first we need to see how do we impose this condition that the global energy is preserved. And one way to do it is to say, well, we apply a global unitary and we need to commute with the total Hamiltonian. And why is that? Because in this case, you'll see that the total energy in the beginning and the total energy at the end is 0. Is the same, sorry. Okay, so let's see this. So we start with some state rho, and we evolve it to be u rho u dagger. And we care about the total energy in the beginning and the total energy at the end, right? And now this could be for any Hamiltonian, not necessarily this kind of system, but this is more general. So let's look at the average energy at the end. Well, this is going to be a trace of Hamiltonian final state. Now, because the H and U commute, I can send U to the other side. So there it is. Because the trace is cyclic, I can send U to the other side here. Okay. But this is, because U is a unitary, this is the identity, so I get trace of H rho, and that's the initial energy. So then I got that the final energy is the same as the initial energy. Good. So this tells us that one way to impose energy conservation is by saying, well, let's say that the overall energy should commute with the Hamiltonian, as overall operation should commute with the Hamiltonian. And what's the total Hamiltonian? In this case, it's non-interactive, right? This is what we want in general, so at least initial and final Hamiltonian. So I have something on S, tensor identity in the battery, plus identity on system, tensor my Hamiltonian of the battery. Hamiltonian of the battery looks like this in general, like we saw. For the system, it depends on the system. In this qubit example that we saw, it looks like this, right? So now we look at this example. Well, let's say we start in this initial state. So we have 0 in the system and a very specific AK, so this energy AK on the battery. And what we want to implement is a qubit flip on the system, a bit flip on the system, right? So something like the X operator. But we want to implement it in an energy conserving way. Okay, so well, in order to find the global operation, it's going to have to be like, if I go from state 1 to 0, so if I go down here, then I need to go up there by some amount that preserves the energy. Okay. So we define here, we want this energy to be the same as the amount that I'll go up here. So I'll just define some number q, which is epsilon divided by these little gaps in the Hamiltonian of my battery. The reason why I wanted these gaps to be very, very small is because I want this q to be an integer number, to correspond to like an integer amount of steps that I need to go up or down on in my battery. Right? So in the limit, we'll have this being, again, the position, just a continuous system. Okay, so here we are. So if I start with 1 and want to go to 0, then what I need to do is to start on some energy level AK and go up by some amount, by this amount q, right? Number of steps. Plus, if I start in 0 and want to go to 1, then I need to go down by the same amount. And this should not depend on the initial state of the battery, so I sum over all case, right? I sum over all possible initial states of the battery. You'll see in the tutorial that this is indeed a Hamiltonian and that indeed it does commute with, that this is a unitary and that it does indeed commute with a Hamiltonian. But for now, we just see that it works. Okay, so we apply this unitary that we saw before to our initial state. So let me get rid of this first. Okay. So what's in dark blue is just the same unitary before, and then I just put the state here in light blue, right? Chuk, chuk. Well, this thing here is an inner product that's 0, which is why, there you go, this is 0. So this whole term disappears. But now on the second part, you have this inner product here, this is 1, right? This is 1. So we have to consider what's happening on this side. Well, and here you have this inner product between a k prime. I just changed the variable name here, and the initial state. So that's just delta k prime. So in the end, out of all these sums, the only one that will survive is the one where this k prime is k. And so I end up here with k minus q. Okay, there we are. So this is the final state of the system. In the first one, I had 1, okay, which corresponds exactly to this. So I had 0, oops. I had 0, I had uk, and now I have 1 here, and I have some uk minus q down there. Okay, so now what we need to compute is the initial energy, the final energy, and so on. Let me just get the charger. Okay, so let's compute the initial energy of the system. So in this case, because the Hamiltonian is really composed of these two different parts, system on one side and the battery on the other side, it's very easy to compute the energy. So we just want to know the trace of this operator, which is HS in the first system, identity in the second, times the whole initial state, which is this state here. Now, because this is a local observable, the easiest way to do it when the initial state is very easy is to just take the partial trace over the battery of the state, and then you're left with just HS here, right? We looked into this. And in this case, it's very simple to take the partial trace because it's a product state. So if I look at the part on the system S, it's just going to be 0. Okay, so we have the trace of Hamiltonian S times 0, but the Hamiltonian S just had a component for this initial state 1. So we'll end up with a 0 here because of this inner product being 0. So the initial energy of the system is 0, which indeed is what we expected. There will be no surprises here. The initial energy of B, we do the same thing. The reduced state on B is Ek, and we already saw that for Ek, the initial energy was delta K. For the total initial energy, we need to have the trace of the total Hamiltonian and the initial state. But the total Hamiltonian, we saw it's the sum of these two parts. So because this trace is linear, we can split it into first the part on the battery and then the part on the system. But this is exactly the things we just computed before. So the average energy of the battery and the average energy of the system, which we just computed to be delta times K plus 0. So we have delta times K. The final energy on the system. So we do again the same thing. What's the final state of the system? It was 1. So the final energy is epsilon. The final energy on the battery, well, the final state was Q minus Q, so it's delta Q minus K, K minus Q. But from the definition of Q, we just get delta K minus epsilon. Okay, so you can see exactly that the energy that went into the system was left from the battery. Okay, so the total final energy, again, we already know that it doesn't change, but we can do it explicitly. It's going to be this energy plus this energy, which is epsilon plus delta Q minus epsilon, so that's just the same as initial energy. Okay. This is a very, very simple, very trivial example, but what it shows is that we can indeed keep track of changes in energy in a system. Okay. And this is the first ingredient that we need in order to do thermodynamics. So in the next lecture now, we're going to see what happens if you bring in another system that is now corresponding to like a hot system, so something at a given temperature. And we'll see how we define like a thermal state, and I'll see what we can do with it. And so some of the things we can do with quantum thermodynamics is, for example, find out how much heat must computers dissipate when they're computing, right? How much must computers heat up due to just the energy they need to do computations. And we find like the ultimate limit to this. We can do things like, can we make a very, very small fridge? So can we make a fridge made only of a few qubits that maybe you could put inside a quantum computer to cool it down? So then how can we engineer such a thing? So these are the kind of things that we will look into, and in much more detail in the course in the next semester in these advanced topics in quantum information theory. Okay, I will stop now. I think this went reasonably well, so I will upload this. Okay, ciao and ngwata.